melting. And this is synonymous with what we'll call equilibrium melting. And it's also a key component here is that it's closed system. Okay. And I should mention that this is also for crystallization. It's exactly the same thing because we're assuming 100% equilibrium. Let me explain what I mean by that. So let's take a box. This is a system. This might be my magma that comes in. And it starts to crystallize. And so you have different crystals in here. Those are the crystals. This part is the melt. And then the circles are the crystals. The whole thing, crystals melt, is the magma. We're going to assume that chemically, the crystals are always in equilibrium with the melt from the core of the crystals all the way to the rim. In reality, if the crystals are growing kind of at time scales faster than elements can diffuse through the crystal, then the core is actually not in communication with the melt, in which case we need to consider a disequilibrium process or a fractional crystallization or a fractional melting process. And we'll do that later. For now, let's consider it's always in communication at all length scales. And so that's why we call it equilibrium melting or equilibrium crystallization. So what we want to do is track a certain trace element through extent of crystallization or melting, and see how it gets enriched or depleted as you get more crystallization. So I guess I'm going to go with crystallization here. And so in all of these problems, we just start off with conservation of mass, right? That's really all you need, conservation of mass. And what we're going to do, we're going to assume that the mass of this whole system is m0, okay? And that, of course, must equal the mass of all the solids plus the mass of the melt, right? And it's because it's a closed system, so that holds at all times. Then what I'm going to do is define these quantities. The mass fraction of the solids is equal to ms, right, over the total mass. Okay. And then the mass fraction of the melt is m total. Okay. And if I divide everything here, that first equation, by m0, then what I'll have is 1 is equal to xs plus xm. Okay. What I'm going to do to keep things simple is I'm going to call this thing F. From now on, this thing is the melt fraction. Okay. So now what we want to do is look at conservation of mass for a particular element, a trace element. Okay. And we're going to define that the concentration, the mass concentration of an element in the crystal or in the melt is given by C. Okay, like it would be in parts per million, weight percent, so forth. So the total mass of an element in my magmatic system would be the concentration average of the total system multiplied by m0, right? and that then must equal the total mass in the solids, so CS ms any given time plus Cm mm, right? Now, if I divide this entire equation by m0, then I will get this equation equals CS 1 minus F plus Cm F. And note here that I've used F in the place of Xm. So 1 minus F is XS right here. So this is right here just the same as the top equation over there. Now we're going to make use of another relationship, which is the partitioning, right, of a trace element between two phases, the solids and the melts. So we denote that with this symbol D. That's the partition coefficient, and that is the concentration in the solid over the concentration in the melt. You always put the solid over the melt, and it's to denote how this element might be distributed between the two phases at equilibrium. Okay. Now, it's empirical, and we'll talk about partition coefficients in another lecture. But when D is not greater than 1, we call this compatible in the middle. And when it is less than 1, it's incompatible. Okay? Some terminology for you. We can then take this and substitute it in here for CS, actually. So CS would be Cm times D, and that will then give you this C0 is equal to D Cm 1 minus F plus Cm F, okay? And we can rearrange all of this to get an equation that expresses how the composition of the melt evolves relative to the bulk concentration of that element as a function of degree of crystallization or melting. That would be this D plus F 1 minus D right here. And this is the batch melting equation, equilibrium crystallization or equilibrium melting. And obviously, at equilibrium, Cm is related to Cs, the solid. So I could write the same form for what the composition in the solid would be. And that's the same, but you multiply it by that, by D. Okay? So now, and this is for the solid. Now, I should note that this partition coefficient really is what we call a bulk partition coefficient. If there are different mineral phases, like under the colors, some here that are dark and some light, this might be clinopyroxene and olivine, say, in the mantle, then the bulk partition coefficient is some sort of weighted average of the partition coefficients of each of the phases. And so D up there is really the sum of the mass fractions of each mineral phase times the D for a given phase. In other words, it might be the fraction of phase A times D phase A plus FB, DB, and so forth, okay? And F right here is with respect to the solid, not the bulk system. So what does this become? Okay. So when you have a multi-solid phase system, you need to account for the different phases. And since it's at equilibrium, you can just use this equation, just use the right bulk D, and you will actually have to correct for how F, these little f's, the mineral or the phase proportions within the solids change as a function of F. If you do that, you're all good. Now, we can look at how this behaves. I'm going to make a plot here of this F right here. This would, over here would be 100% melt. And over here would be no melt or 0% melt. So it's fully crystallized, okay? And we can consider these scenarios, and the y-axis is Cn over C0. Okay? If D equals 1 in this equation right here, right, then Cm and C0 cannot change. And that should not be a surprise to you, because if it's 1, then nothing should change. So this line, 1, I'll call this 1, is D equals 1. When D is less than 1, the element is incompatible, and so with progressive crystallization, it should become more and more enriched in the melt. And if D is greater than 1, so this D is less than 1 would be here, and D greater than 1 obviously would be here. The melt will become depleted with progressive crystallization, because the crystals keep taking away that compatible element. Now we can look at when the case F equals 1 in this same equation. When F equals 1, then this quantity becomes 1 as well. That means when you melt it 100%, you should get to the bulk composition, right? So all these curves should converge to 1 at F equals 1. Now we can consider a case where D is 0, perfectly incompatible. And when D equals 0, this equation, if I say D equals 0, then Cm C0 should equal 1 over F. So the maximum enrichment that you can ever get is when something is perfectly incompatible and is controlled by the degree of how much melt you have. So when F equals 1, no enrichment. When F is, like, say, 10% or 0.1, you have a tenfold enrichment. So this would be the case for D equals 0. And you can't really get above that line, but you can see when F goes to very small, this goes up to infinity. So you can get extreme enrichments if you keep crystallizing to the point you have almost only an infinitesimal amount of residual melt. But for any given F, you cannot exceed the D equals 0 line. If it's compatible, then what you'll get in the melt is something that looks like this. Also will converge to 1 at F equals 1. But the value over here is then equal to 1 over D, okay? When F equals 0. And the same thing goes for up here, right? Obviously when D equals 0, this goes to infinity. but when D is finite, it's somewhere in between. Okay. Now, the solids, if I were to plot the same solids on the same scale, now C solid, C0, there, what you'll get, and this being 1, this is F, you will get a curve like that for D greater than 1, and then like this for D less than 1. So it's just the reverse. Okay. Where this can become useful for you is if you go and look at a magmatic system. Often you might plot like in an arc, like a arc system, volcanic arc. And I may plot SiO2, I plot K2O, and often you'll see an array that looks like this. And it turns out potassium, up until you get to very high potassium content, is actually almost perfectly incompatible. Silica is not. But if potassium is perfectly compatible and you start off and say something here is your C0, and you're looking at here like a rhyolite, C melt, then you can then calculate the Cn over C0, approximately 1 over F. We can probably calculate then how much crystallization from a parental magma is needed to give you a rhyolite, if the rhyolite is formed by such a process. And so you should check this out on your own, but if the enrichment factor from the parent to the rhyolite is about 10, right? And what that means is to get a rhyolite from over here, a basalt, this is rhyolite, basalt, you're going to need about 90% crystallization. So if you see 1 kilometers of rhyolite, which you really never do, but let's say you do, then you're going to need 10 times more cumulates or everything else down hidden at depth.